Welcome to Sleepy Science Odyssey. Tonight, the Milky Way, our home galaxy, a vast spiral of stars, gas, and dust stretching across 100,000 light-years. We'll move slowly through its structure, from the dense core to the sparse outer halo, exploring the billions of stars that share this cosmic island with us. We'll travel through spiral arms, visit ancient star clusters, examine the supermassive black hole at the center, and trace the history of this galaxy from its birth over 13 billion years ago to its eventual merger with Andromeda billions of years in the future. If you're new here, this channel is for people who need something to think about before they can stop thinking. Real science, no hype, just quiet facts in the dark. Let's begin. The Milky Way is a barred spiral galaxy. From above, if you could somehow position yourself high above the galactic plane and look down, the Milky Way would look like a pinwheel with a central bar-shaped structure of stars. Two major spiral arms curve outward from the ends of this bar, with several smaller arms branching off between them. The entire structure rotates, though not like a solid disk. Different parts orbit at different speeds, creating a complex dynamic system. Stars near the center complete an orbit in a few million years, racing around the galactic core. Stars farther out, like the Sun, take much longer, about 225 million years to complete one orbit. This differential rotation is what creates and maintains the spiral arms, as stars and gas move through regions of higher density, slowing down briefly before speeding up again. The galaxy is not a rigid object frozen in space. It's a dynamic, evolving system, constantly in motion, with each star following its own orbital path around the galactic center. The shape we see is a snapshot, a moment in a process that has been ongoing for over 13 billion years and will continue for billions more. The bar at the center likely formed within the last few billion years, created by gravitational instabilities in the disk. Bars are common in spiral galaxies. About 2/3 of spirals have them, and they play an important role in galactic evolution, channeling gas toward the center and influencing star formation. The Milky Way contains between 100 and 400 billion stars. The exact number is uncertain, and estimates vary depending on the methods used and assumptions made. Much of the galaxy is hidden from our view by dust clouds that block visible light, especially toward the galactic center. We can't see every star, so astronomers estimate the total based on the stars we can observe, models of galactic structure, and comparisons with other galaxies. Even the lower estimate, 100 billion stars, is almost incomprehensible. If you counted one star per second without stopping, it would take over 3,000 years to count them all. If every person on Earth counted stars simultaneously, we'd finish in just a few hours, but of course, we can't see them all. The number includes all types of stars, from tiny red dwarfs barely massive enough to fuse hydrogen, to massive blue giants burning through their fuel in a few million years. Most stars in the Milky Way are red dwarfs, accounting for perhaps 75% of the total. These small, dim stars are invisible to the naked eye, even the nearest ones, but they dominate the stellar population. The Milky Way also contains white dwarfs, neutron stars, and stellar mass black holes, the remnants of dead stars. These are even harder to detect than red dwarfs, but they're part of the galaxy's population. When we say the Milky Way contains 100 to 400 billion stars, we're including all of these, creating a picture of incredible diversity and scale. Our solar system sits in a minor spiral arm called the Orion Arm. It's sometimes called the Orion Spur because it's not one of the major arms like the Perseus Arm or the Sagittarius Arm. The Orion Arm is a smaller structure, a segment connecting the larger arms, though it's still thousands of light-years across. We're located about 26,000 light-years from the galactic center, roughly halfway out from the center to the edge of the visible disk. This is a fairly typical location, not in the crowded center, not in the sparse outer regions, but in a moderately populated zone where star formation continues at a steady rate. The Sun orbits the galactic center at about 828,000 kilometers per hour, which sounds incredibly fast, but translates to only about 230 kilometers per second in more familiar units. Even at this tremendous speed, it takes approximately 225 million years to complete one orbit. This period is sometimes called a cosmic year or a galactic year. The last time the Sun was in this position, dinosaurs were just beginning to dominate Earth. The next time it returns to this spot, Earth may be unrecognizable or even uninhabitable. The Sun has completed about 20 to 25 orbits since it formed 4.6 billion years ago, circling the galaxy again and again, a passenger on the Great Wheel. Our position in the Orion Arm puts us in a relatively safe zone. We're far enough from the galactic center to avoid the intense radiation and frequent supernova explosions that occur there. We're also not in one of the major spiral arms, where star formation is more active and supernovae more common. Our location may have been crucial for the development of life on Earth, providing a stable environment for billions of years. The Milky Way is about 13.6 billion years old. It formed not long after the Big Bang, which occurred about 13.8 billion years ago. The galaxy coalesced from the primordial gas left over from the Big Bang, enriched slightly by the first generation of stars that formed and died in the early universe. These population III stars, as they're called, were made only of hydrogen and helium, with no heavier elements. They lived briefly and exploded as supernovae, scattering the first carbon, oxygen, and iron into space. This enriched gas began to collapse under gravity, forming the proto-Milky Way. The oldest stars in the galaxy, found in the halo and globular clusters, are nearly as old as the galaxy itself, with ages of 13 to 13.6 billion years. These ancient stars formed when the galaxy was young, before the disk had fully settled and before the spiral structure developed. Over billions of years, the Milky Way has grown and evolved, merging with smaller galaxies and forming new stars from the material left behind by dying ones. The galaxy we see today is the result of 13.6 billion years of evolution, a mature spiral galaxy in the prime of its life. But it's still changing, still evolving. Star formation continues in the disk. New stars are born each year, and old stars die, returning their material to the interstellar medium. The Milky Way is not a static object, but a living system, continuously recycling matter through generations of stars. The galactic disk is surprisingly thin. The Milky Way is about 100,000 light-years across, but the main disk, where most stars reside, is only about 1,000 light-years thick in the plane of the spiral arms. If you scaled the galaxy down to the size of a dinner plate, the disk would be thinner than a sheet of paper. Most of the galaxy's stars, including the Sun, orbit within this thin disk, following nearly circular paths around the galactic center. The disk is where active star formation occurs, where gas clouds collapse and new stars ignite. It's divided into two components, the thin disk and the thick disk. The thin disk, where the Sun resides, is about 1,000 light-years thick and contains young stars, gas, and dust. The thick disk, above and below the thin disk, is about 3,000 light-years thick and contains older stars with higher velocities perpendicular to the plane. These stars bob up and down as they orbit, crossing through the galactic plane every few tens of millions of years. The origin of the thick disk is still debated. It may have formed from stars kicked out of the thin disk by gravitational interactions, or it may be the remnant of a satellite galaxy that merged with the Milky Way long ago. The thinness of the disk makes it vulnerable to disturbances. A collision with even a small galaxy can warp or disrupt the disk, creating ripples that persist for billions of years. The Milky Way's disk shows evidence of such disturbances, with a slight warp in the outer regions that may be caused by the gravitational influence of satellite galaxies like the large Magellanic Cloud. At the center of the Milky Way is a supermassive black hole. It's called Sagittarius A, pronounced Sagittarius A star, and it sits at the exact center of the galaxy, the point around which everything else orbits. This black hole has a mass of about 4.15 million times that of the Sun, all compressed into a region smaller than Mercury's orbit around the Sun. The event horizon, the point of no return, is about 12 million kilometers in radius, roughly 17 times the radius of the Sun. Despite its enormous mass, Sagittarius A is relatively small by supermassive black hole standards. The black hole in the galaxy M87, famously imaged by the Event Horizon Telescope, has a mass of about 6.5 billion solar masses. Still, Sagittarius A dominates the gravitational landscape of the galactic center, holding sway over the motions of nearby stars. We can't see the black hole itself because it emits no light, but we can detect it through the motion of stars around it. Stars near Sagittarius A orbit at incredible speeds. One star, designated S2, completes an orbit in just 16 years, reaching speeds of up to 3% the speed of light at its closest approach. By tracking these orbits using telescopes like the Very Large Telescope in Chile, astronomers have precisely measured the mass of Sagittarius A and confirmed that it's a black hole. The discovery earned Reinhard Genzel and Andrea Ghez the 2020 Nobel Prize in Physics. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A, showing the glowing ring of gas surrounding the dark central region where the black hole resides. The image confirmed predictions from general relativity and provided direct visual evidence of the black hole's existence. The galactic center is incredibly crowded. Within a single light-year of Sagittarius A, there are millions of stars packed together. For comparison, the nearest star to our Sun is over 4 light-years away. Near the galactic center, stars are separated by distances measured in light weeks or light days, not light years. The stellar density is about 1 million times higher than in the solar neighborhood. If Earth were located near the galactic center, the night sky would be spectacular. Thousands of stars would be brighter than Venus appears from Earth. The sky would never be truly dark. Many stars would be bright enough to cast shadows, and the combined light of all those stars would create a perpetual twilight, even when the sun was down. But this crowded environment would also be hazardous. Close encounters with other stars would be common, potentially disrupting the orbits of planets in the outer solar system, or even ejecting planets from the system entirely. The intense radiation from nearby stars and the supermassive black hole would bathe planets in high-energy particles, making the surface inhospitable for life as we know it. The galactic center is also home to massive star clusters, dense collections of stars orbiting close to Sagittarius A. One cluster, the Arches cluster, contains some of the most massive stars in the galaxy, each dozens of times the Sun's mass, burning intensely and destined to explode as supernovae within a few million years. The environment near the galactic center is dynamic, violent, and unlike anywhere else in the galaxy. It's a region of extremes where gravity, radiation, and stellar evolution operate at their most intense. We can't see the galactic center in visible light. Dust clouds along the galactic plane absorb and scatter visible light. When we look toward the center in visible wavelengths, we see clouds of dust rather than stars. The galactic center is hidden behind about 30 magnitudes of extinction, meaning visible light is dimmed by a factor of 1 trillion. This makes it impossible to observe the center directly in optical wavelengths, but infrared light and radio waves can penetrate the dust. Infrared photons have longer wavelengths than visible light and are less affected by dust grains. Radio waves have even longer wavelengths and pass through dust clouds almost unimpeded. By observing at these wavelengths, astronomers have mapped the galactic center, revealing the dense cluster of stars, the supermassive black hole, and the complex structures of gas and dust surrounding it. The Spitzer Space Telescope, an infrared observatory, captured stunning images of the galactic center, showing millions of stars in invisible light. Radio telescopes have detected complex filaments of gas and magnetic fields, along with the radio emission from Sagittarius A itself. The center of the galaxy is bright in X-rays, produced by hot gas and high-energy processes near the black hole. Observing the galactic center requires using the full electromagnetic spectrum, from radio waves to gamma rays, to build a complete picture. Each wavelength reveals different aspects of this complex environment. Visible light shows us almost nothing, but together, infrared, radio, X-ray, and gamma-ray observations reveal a dynamic, energetic region at the heart of our galaxy. The Milky Way has a halo. This is a roughly spherical region surrounding the galaxy, much larger than the disk. The halo extends out to at least 200,000 light-years from the galactic center, perhaps farther. It's sparsely populated, containing only about 1% of the galaxy's stars, but it's where most of the galaxy's mass resides in the form of dark matter. The stellar halo contains old, metal-poor stars, some of the first generation formed in the Milky Way. These population II stars have very few elements heavier than hydrogen and helium, reflecting the composition of the early universe before supernovae had enriched the interstellar medium. Globular clusters, ancient spherical collections of hundreds of thousands of stars, orbit in the halo. The Milky Way has about 150 known globular clusters, with ages of 10 to 13 billion years. They're among the oldest structures in the galaxy. The halo also contains streams of stars, remnants of satellite galaxies that were torn apart by the Milky Way's gravity. These streams trace the orbits of the disrupted satellites, winding through the halo like ribbons. Detecting these streams is difficult because the stars are so sparse, but surveys like the Sloan Digital Sky Survey and Gaia have revealed dozens of them, each representing a past merger. The dark matter halo dominates the mass of the galaxy. It's estimated that dark matter makes up about 90% of the Milky Way's total mass, far outweighing the visible stars, gas, and dust. This dark matter doesn't emit, absorb, or reflect light, so we can't see it directly. We know it exists only through its gravitational effects. The flat rotation curve of the galaxy, the fact that stars in the outer regions orbit at roughly the same speed as those closer in, is evidence for dark matter. Without it, stars farther out should orbit more slowly, just as outer planets in the solar system orbit more slowly than inner planets. The fact that they don't indicates the presence of additional, invisible mass. Globular clusters orbit in the galactic halo. These are ancient, spherical collections of stars, each containing hundreds of thousands or even millions of stars tightly packed into a region only about 100 light-years across. The Milky Way has about 150 known globular clusters, though there may be more hidden behind dust or too faint to detect. Globular clusters are among the oldest objects in the galaxy, with ages of 10 to 13 billion years, comparable to the age of the Milky Way itself. The stars in globular clusters are metal-poor, containing very few elements heavier than hydrogen and helium. This indicates they formed early in the galaxy's history, before supernovae had enriched the interstellar medium with heavy elements. The clusters orbit the galactic center in elongated, highly elliptical orbits, taking them far out into the halo and then plunging back toward the center. Some globular clusters have orbits that take them well beyond the visible disk, out to distances of 100,000 light-years or more. Others have orbits that bring them relatively close to the Sun, making them visible through small telescopes. Messier 13, the great globular cluster in Hercules, is visible to the naked eye from dark locations and is stunning through binoculars or a telescope. It contains about 300,000 stars packed into a sphere about 145 light-years across. From a planet in M13, the night sky would be filled with bright stars, thousands of them closer than the nearest star is to the Sun. Globular clusters are fossils from the early galaxy, preserved almost unchanged for billions of years. Studying them provides insights into the conditions in the early Milky Way and the formation of the first stars. The Milky Way is not alone. It's part of a group of galaxies called the Local Group, a collection of about 80 galaxies bound together by gravity. This group spans about 10 million light-years, a relatively small region on cosmic scales. The three largest galaxies in the Local Group are the Milky Way, the Andromeda Galaxy, M31, and the Triangulum Galaxy, M33. The Milky Way and Andromeda are the dominant members, each about twice as massive as Triangulum. The rest of the Local Group consists of dwarf galaxies, small collections of stars ranging from a few million to a few billion. Many of these dwarfs are satellites of the Milky Way or Andromeda, orbiting the larger galaxies much as the Moon orbits Earth. The Large Magellanic Cloud and Small Magellanic Cloud are the largest satellites of the Milky Way, visible from the southern hemisphere as fuzzy patches of light. These irregular dwarf galaxies contain billions of stars and are undergoing active star formation. They orbit the Milky Way at distances of about 163,000 and 200,000 light-years, respectively. The Local Group is held together by the mutual gravitational attraction of its members. Gravity on these scales is stronger than the expansion of the universe, so the Local Group is gravitationally bound and won't expand. Instead, its members orbit each other, with the smaller galaxies gradually spiraling toward the larger ones. Over time, the Milky Way and Andromeda will consume most of the smaller galaxies in the group, growing larger and more massive. The Milky Way is on a collision course with Andromeda. Andromeda, also known as M31, is currently about 2.5 million light-years away and moving toward us at roughly 110 kilometers per second. This might sound fast, but given the enormous distance, it will take about 4 billion years for the two galaxies to collide. The collision won't be a violent crash in the way we usually think of collisions. Galaxies are mostly empty space. The stars are so far apart that actual stellar collisions will be extremely rare. Instead, the galaxies will pass through each other, their shapes distorted by gravity. Stars and gas will be pulled into long tidal tails, stretching millions of light-years into space. the spiral structure of both galaxies will be destroyed. The collision will trigger bursts of star formation as gas clouds collide and compress, igniting new generations of stars. The supermassive black holes at the centers of both galaxies will eventually merge, releasing an enormous amount of energy in the form of gravitational waves. Over hundreds of millions of years, the galaxies will swing around each other, coming together and moving apart multiple times. Each passage will distort them further, mixing their stars and gas. Eventually, about 6 to 7 billion years from now, they'll settle into a single, larger galaxy. This merged galaxy will be an elliptical galaxy, a smooth, featureless ball of stars with no spiral structure. Astronomers have given this future galaxy informal names like Milkomeda or Milkdromeda, combining the names of the two progenitors. The merger will reshape the local group, creating a single dominant galaxy that will gradually consume the remaining smaller galaxies. The merger with Andromeda will reshape both galaxies. The Milky Way's delicate spiral structure will be erased. Andromeda's structure will be destroyed as well. The two galaxies will pull on each other with gravity, creating enormous tidal forces that stretch and distort them. Computer simulations of the merger show that long streams of stars will be flung out into space, forming tidal tails that extend for hundreds of thousands of light years. These tails are common in galaxy mergers and can be seen in many interacting galaxies observed by telescopes. The merger will also funnel gas toward the centers of both galaxies, feeding the supermassive black holes and triggering intense star formation. For a brief period, measured in hundreds of millions of years, the merged system will be a starburst galaxy, forming stars at a rate 10 or even 100 times faster than the current rate in the Milky Way. This burst will consume much of the remaining gas, leaving the merged galaxy with little fuel for future star formation. After the starburst phase ends, the galaxy will settle into a more quiescent state, dominated by old, red stars. The Sun and Solar System will likely survive the merger. The chances of a direct collision with another star are minuscule, perhaps 1 in a billion, but our position in the galaxy will change. Gravitational interactions during the merger will fling stars to new locations. The Sun might end up in the outer halo of the merged galaxy, or it might settle into a more central orbit. From Earth, if it still exists, the night sky during the merger will be spectacular. Andromeda will grow larger and larger as it approaches, eventually filling a significant portion of the sky. During the closest passages, the sky will be filled with stars from both galaxies, and the tidal tails will stretch across the heavens like glowing arcs. The Milky Way has satellite galaxies. These are smaller galaxies that orbit the Milky Way, held by its gravity. The largest are the large and small Magellanic Clouds, irregular dwarf galaxies visible from the southern hemisphere. The Large Magellanic Cloud, LMC, contains about 30 billion stars, while the Small Magellanic Cloud, SMC, contains about 3 billion. Both are undergoing active star formation, with massive young stars and glowing nebulae visible in telescopes. The LMC is about 163,000 light-years away, while the SMC is about 200,000 light-years away. To observers in the southern hemisphere, they appear as fuzzy patches of light, like detached pieces of the Milky Way. Other satellites are much smaller and fainter. Dwarf spheroidal galaxies like Sculptor, Fornax, and Carina contain only a few million stars and are so faint they were discovered only in the 20th century. Some satellites are even smaller, containing only a few thousand stars, barely qualifying as galaxies. These ultra-faint dwarfs were discovered in the 21st century using sensitive surveys that can detect extremely faint objects. In total, the Milky Way has dozens of known satellite galaxies, and there may be more waiting to be discovered, hidden in the halo or behind the galactic plane. These satellites are gradually being torn apart by the Milky Way's gravity. Tidal forces strip stars from the satellites, forming streams that orbit the galaxy. The Sagittarius Dwarf Elliptical Galaxy, one of the closest satellites at about 70,000 light-years away, is currently being disrupted. Its stars form a stream that wraps around the Milky Way, visible as an enhancement in star density across large parts of the sky. Eventually, the Sagittarius Dwarf will be completely consumed, its stars absorbed into the Milky Way's halo. This process of galactic cannibalism is common. Large galaxies grow by consuming smaller ones, and the Milky Way has likely consumed dozens of satellites over its history. The Large Magellanic Cloud is about 163,000 light-years away. It's one of the closest galaxies to the Milky Way and has been known to humans for millennia. Ancient astronomers in the southern hemisphere documented it, though they didn't understand what it was. To observers south of the equator, it looks like a faint, fuzzy cloud, visible to the naked eye even from moderately light-polluted areas. The Large Magellanic Cloud is an irregular dwarf galaxy, lacking the spiral or elliptical structure of larger galaxies. It's undergoing active star formation, with massive young stars and bright nebulae. The Tarantula Nebula, located in the LMC, is one of the most active star-forming regions known, containing thousands of newly formed stars and several of the most massive stars in the local universe. The LMC also hosted supernova 1987A, the closest supernova to Earth since the invention of the telescope. When it exploded in 1987, it reached naked-eye visibility and was extensively studied by astronomers. The data from SN 1987A provided unprecedented insights into supernova physics, neutrino emission, and the formation of neutron stars. The Large Magellanic Cloud is thought to be a satellite galaxy orbiting the Milky Way, though its exact orbit is still uncertain. It may be on its first passage past the Milky Way, having been drawn in from a greater distance, or it may have orbited the Milky Way multiple times. The interaction between the LMC and the Milky Way is complex. The LMC's gravity affects the Milky Way's disk, contributing to the warp observed in the outer regions. As the LMC orbits, it loses gas and stars to the Milky Way, contributing to the larger galaxy's growth. In the far future, the LMC may merge with the Milky Way, adding its mass to ours and triggering bursts of star formation. The Small Magellanic Cloud is slightly farther away, at about 200,000 light-years. It's smaller and fainter than the Large Magellanic Cloud, but still visible to the naked eye from the southern hemisphere. The Small Magellanic Cloud, SMC, is also an irregular dwarf galaxy with active star formation. Like its larger companion, it's been known since ancient times and features prominently in the mythology and astronomy of southern hemisphere cultures. The SMC contains about 3 billion stars and has a complex structure. It's being distorted by the Milky Way's gravity and by interactions with the Large Magellanic Cloud. A stream of gas connects the two Magellanic Clouds, evidence that they're interacting with each other as well as with the Milky Way. This stream, called the Magellanic Bridge, contains gas stripped from both galaxies by tidal forces. There's also a larger structure called the Magellanic Stream, a long trail of gas stretching across much of the southern sky, wrapping around the Milky Way. This stream was stripped from the Magellanic Clouds during their orbit, leaving a trail of gas behind them like a comet. The Magellanic Stream is one of the largest structures associated with the Milky Way, spanning more than 100 degrees across the sky and containing about 200 million solar masses of gas. Studying the Magellanic Clouds and their interactions with the Milky Way provides insights into how large galaxies grow by consuming smaller ones. The clouds are in the process of being accreted, and in a few billion years, they'll likely merge completely with the Milky Way, their stars and gas becoming part of the larger galaxy. The Milky Way's spiral arms are not permanent structures. They're density waves, regions where stars and gas temporarily bunch together as they orbit. Think of them like traffic jams on a highway. Cars slow down, bunch together in the jam, and then speed up again as they exit. The traffic jam itself moves at a different speed than the cars, persisting even as individual cars pass through it. Similarly, stars enter a spiral arm, slow down slightly, and then exit on the other side. The arm itself persists even as individual stars pass through it, maintained by the collective gravitational influence of all the stars and gas in the galaxy. This is why spiral arms are sites of active star formation. As stars and gas enter the arm, the increased density compresses gas clouds, triggering their collapse and the formation of new stars. The bright blue stars we see in spiral arms are young, massive stars that formed recently and are still in or near the arms. These stars don't live long enough to travel far from where they formed before they die as supernovae. Older, cooler red and yellow stars, like the Sun, have had time to drift away from the arms and are found throughout the disk. The spiral pattern itself rotates, but at a different speed than the stars. This differential rotation is what maintains the spiral structure. If the spiral arms rotated at the same speed as the stars, they would wind up over time, becoming tighter and tighter until they disappeared. Instead, the pattern rotates independently, allowing the spiral structure to persist for billions of years. The exact mechanism that creates and maintains spiral arms is still not fully understood, but density wave theory, developed in the 1960s, explains many of the observed features. The Sun has completed about 20 to 25 orbits around the galaxy. It formed about 4.6 billion years ago, and each orbit takes roughly 225 million years. So the Sun has been around the galaxy a little over 20 times, though the exact number depends on small variations in the orbital period over time. Each time it completes an orbit, it returns roughly to the same position, though not exactly. The gravitational influence of other stars, the spiral arms, and the overall structure of the galaxy cause slight variations in the orbit. The Sun's orbit is not a perfect circle but slightly elliptical, and it bobs up and down through the galactic plane as it travels. Currently, the Sun is about 60 light-years above the galactic plane and is moving upward. In about 14 million years, it will reach its maximum height, about 250 light-years above the plane, then fall back through the plane and continue to about 250 light-years below before rising again. This oscillation has a period of about 60 million years. As the Sun orbits, it passes through the spiral arms, spending about 10 million years in each arm and then moving into the interarm regions. Some scientists have speculated that these passages through the spiral arms might affect Earth's climate or increase the rate of comet impacts, but the evidence for such effects is weak. The Sun has witnessed the galaxy change over billions of years, though of course it has no memory. It's simply been along for the ride, orbiting steadily while the galaxy evolved around it. During the Sun's lifetime, the galaxy has likely consumed several satellite galaxies, experienced multiple bursts of star formation, and seen billions of stars born and die. The Milky Way is shaped by dark matter. Visible matter, stars, gas, and dust, makes up only about 10% of the galaxy's total mass. The rest is dark matter, an invisible substance that doesn't interact with light. We know it's there because of its gravitational effects. Stars in the outer regions of the galaxy orbit faster than they should based on the visible mass alone. According to Newton's laws and Kepler's laws, stars farther from the center should orbit more slowly, just as outer planets in the solar system orbit more slowly than inner planets. But observations show that stars in the outer Milky Way orbit at roughly the same speed as stars closer in. This flat rotation curve can only be explained if there's additional, unseen mass providing extra gravity. That additional mass is dark matter, distributed throughout the galactic halo and extending far beyond the visible disk. The dark matter halo may extend out to 600,000 light-years or more from the galactic center, many times larger than the visible galaxy. Dark matter dominates the mass of the Milky Way and shapes its gravitational potential. It affects the orbits of stars, the motion of satellite galaxies, and the overall structure of the galaxy. Without dark matter, the Milky Way would look and behave very differently. Spiral arms might not exist or would be much less prominent. Satellite galaxies would have different orbits. The galaxy might not even hold together. Without the extra gravity from dark matter, stars in the outer regions might escape into intergalactic space. Dark matter is one of the biggest mysteries in astrophysics. We don't know what it's made of. It could be composed of unknown subatomic particles, or it could be something entirely different. Experiments around the world are searching for dark matter particles, trying to detect them directly. So far, none have succeeded, and dark matter remains elusive. The fastest stars in the galaxy are near the center. Stars within a light-year of Sagittarius A orbit at speeds exceeding 5,000 kilometers per second, about 1.7% the speed of light. One star, designated S2, has been observed completing an orbit in just 16 years. Its closest approach to the black hole brings it within 17 light-hours, about 120 times the distance from Earth to the Sun. At that distance, the star experiences extreme gravitational forces and travels at about 3% the speed of light at perihelion, the point of closest approach. The orbit of S2 has been used to test Einstein's theory of general relativity in an extreme environment. Observations showed that the orbit shifts slightly each time, a phenomenon called orbital precession, exactly as predicted by general relativity. The star's light is also gravitationally redshifted as it climbs out of the black hole's gravitational well, another prediction of general relativity confirmed by observations. These measurements are only possible because the star is relatively bright, and its orbit has been tracked for over 25 years using some of the world's most powerful telescopes. Other stars near the galactic center are too faint or too embedded in the dense stellar background to track individually, but their collective motions reveal the presence of the supermassive black hole and provide information about the mass distribution in the central region. The environment near Sagittarius A is one of the most extreme places in the galaxy, a natural laboratory for testing physics in strong gravitational fields. The Milky Way is producing new stars. Star formation occurs primarily in the spiral arms, where gas clouds are compressed and collapse. The rate of star formation in the Milky Way is about 1 to 3 solar masses per year. That means every year, enough gas is converted into stars to equal the mass of 1 to 3 suns. This might sound like a lot, but the galaxy contains so much gas that it can sustain this rate for billions of years. However, star formation is gradually slowing as the galaxy consumes its gas reserves. The Milky Way has about 10 billion solar masses of gas available for star formation, mostly in the form of molecular hydrogen. At the current rate, this gas will be exhausted in a few billion years. Star formation is not distributed evenly across the disk. It's concentrated in the spiral arms and in specific star-forming regions like the Carina Nebula and the Orion Nebula. These regions contain dense molecular clouds where conditions are right for collapse. The clouds are cold, about 10 to 20 Kelvin, and dense by interstellar standards, with hundreds to thousands of particles per cubic centimeter. That's still far more tenuous than the best vacuum achievable on Earth, but it's dense enough for gravity to overcome the internal pressure and cause collapse. Once a region begins to collapse, it fragments into many smaller clumps, each of which can form a star. The result is that stars typically form in groups, not isolation. Most stars are born with siblings, though many drift apart over time. The Milky Way contains vast clouds of hydrogen gas. These clouds, called HII regions when ionized by nearby stars, are the raw material for star formation. One of the largest is the Carina Nebula, about 8,500 light-years away. It's a massive star-forming region, home to some of the most luminous and massive stars known, including Eta Carini, a star over 100 times the mass of the Sun. The nebula glows with the light of these young stars, their intense ultraviolet radiation ionizing the surrounding gas and causing it to emit light. The Carina Nebula is so large that if it were as close to us as the Orion Nebula, it would span 30 degrees across the sky, 60 times the width of the full moon. It would dominate the night sky, visible even from light-polluted cities. Other notable HII regions include the Lagoon Nebula, the Eagle Nebula, home to the famous Pillars of Creation, and the Omega Nebula. Each is a stellar nursery, a place where stars are being born. These regions are often beautiful in photographs, with intricate structures carved by stellar winds and radiation. Dark pillars of dust stand out against glowing gas, and young stars shine like jewels embedded in the nebula. But the beauty is transient. The radiation from the newborn stars gradually disperses the remaining gas, blowing it away and destroying the nebula. In a few million years, the gas will be gone, and only the stars will remain, a new cluster slowly drifting through the galaxy. The galactic plane is filled with dust. This dust, made of tiny grains of carbon and silicate, absorbs and scatters light. The grains are only a few microns across, about the size of smoke particles, but there are enough of them to block light from distant stars. It's why we can't see through the galaxy in visible light. The dust also emits infrared light when warmed by starlight, making the galactic plane bright when viewed in infrared. This infrared glow comes from the dust grains themselves, heated to temperatures of a few tens of Kelvin by the diffuse starlight permeating the galaxy. Infrared telescopes like the Spitzer Space Telescope and the now-retired Herschel Space Observatory have mapped this dust glow in exquisite detail, revealing the distribution of dust throughout the galaxy. Dust isn't just an obstacle, it's essential for star formation. Dust grains provide surfaces where molecules can form, allowing hydrogen atoms to combine into molecular hydrogen, the fuel for star formation. Dust also shields the interiors of gas clouds from destructive ultraviolet radiation, allowing them to cool and collapse into stars. Without dust, star formation would be much less efficient, and the galaxy would look very different. Dust is created by stars. Red giants and supergiants, cool evolved stars, have extended atmospheres where dust can condense from gas. Supernovae also create dust, forging grains in the expanding ejecta. This dust is then mixed into the interstellar medium, enriching the galaxy and becoming incorporated into the next generation of stars and planets. The dust in the Earth, the dust in your house, the dust floating in a sunbeam, it all ultimately came from stars. The Milky Way has a warp. The galactic disk isn't perfectly flat. It bends and twists, especially in the outer regions, like the brim of a hat that's been sat on. The warp causes the disk to curve upward on one side and downward on the other, with the maximum deviation occurring at distances greater than about 50,000 light-years from the galactic center. The cause of this warp is still debated. It may be due to gravitational interactions with satellite galaxies like the Magellanic Clouds. As these satellites orbit the Milky Way, their gravity tugs on the disk, distorting its shape. Alternatively, the warp could be the result of the galaxy's dark matter halo having an irregular shape, causing uneven gravitational forces on the disk. The warp is subtle, only a few thousand light-years in amplitude, but it's measurable. It was first detected in the 1950s through observations of neutral hydrogen gas using radio telescopes. The hydrogen in the outer disk is displaced vertically from the plane by amounts that vary with position, creating the characteristic S-shape of a warped disk when viewed edge-on. More recent observations, including data from the Gaia spacecraft, have mapped the warp in 3 dimensions using the positions of stars. The warp is a common feature of spiral galaxies. Many spirals show similar distortions in their outer disks, suggesting that warps are a natural consequence of galaxy evolution and interactions with satellites. The local bubble is a cavity in the interstellar medium. The Sun is currently passing through a region of space about 300 light-years across where the gas density is much lower than average. This bubble, called the local bubble or local cavity, was likely created by supernova explosions from a group of massive stars that formed and died nearby within the last 10 to 20 million years. The explosions swept up the surrounding gas, compressing it into a shell and leaving behind a hot, low-density cavity. The Sun entered the local bubble about 5 million years ago and will remain inside it for another few million years as it orbits the galaxy. Inside the bubble, the interstellar medium is hot, about 1,000,000 Kelvin, but extremely tenuous, with densities of only about 0.005 particles per cubic centimeter. That's even more tenuous than the average interstellar medium, which itself is far more rarefied than the best vacuum achievable on Earth. The local bubble is part of a larger structure of cavities and shells created by stellar winds and supernovae. These bubbles permeate the disk, giving the interstellar medium a complex, frothy structure. The Sun's passage through the local bubble may have effects on Earth's environment. The lower density of interstellar material means less shielding from cosmic rays, potentially increasing the flux of high-energy particles reaching the solar system. Some scientists have speculated that this could affect Earth's climate or the rate of genetic mutations, but the evidence for such effects is weak and controversial. The Milky Way has experienced mergers in the past. Smaller galaxies have collided with and been absorbed by the Milky Way over its history. Evidence of these mergers can be seen in streams of stars that crisscross the galactic halo, remnants of dwarf galaxies that were torn apart by tidal forces. One such stream, the Sagittarius Stream, is the remains of the Sagittarius dwarf elliptical galaxy, which is currently being consumed by the Milky Way. The stream wraps around the galaxy multiple times, with stars from the disrupted dwarf spread across large portions of the sky. Other streams have been discovered using data from surveys like the Sloan Digital Sky Survey and the Gaia mission. These streams are named after constellations in the regions where they're most prominent: the Helmi Stream, the Virgo Stellar Stream, the Orphan Stream. Each represents a past merger, a satellite galaxy that was pulled apart and absorbed. The most significant merger in the Milky Way's recent history occurred about 10 billion years ago, when a galaxy called Gaia Enceladus collided with the Milky Way. This merger added stars to the halo and possibly contributed to the formation of the thick disk. Evidence for the merger comes from the motions and chemical compositions of stars in the halo, which show patterns consistent with having originated in a separate galaxy. The merger may also have triggered a burst of star formation in the Milky Way, adding to the population of stars in the disk. These mergers are a normal part of galaxy evolution. Large galaxies grow by consuming smaller ones, and the Milky Way has likely consumed dozens of satellites over its history. The process continues today, with several satellites currently being disrupted and absorbed. The Milky Way's central bar is relatively recent. The bar, a dense concentration of stars running through the galactic center, likely formed within the last few billion years, possibly as recently as 2 billion years ago. Bars are common in spiral galaxies, about 2/3 have them, and they arise from gravitational instabilities in the disk. Once a bar forms, it can channel gas toward the galactic center, fueling star formation and feeding the central black hole. The bar also affects the orbits of stars, creating resonances that help maintain the spiral arms. The Milky Way's bar is about 27,000 light-years long and rotates about once every 200 million years, faster than the rotation of stars at the sun's distance. The bar's rotation creates a pattern that moves through the disk, affecting the distribution of stars and gas. Stars near the ends of the bar experience stronger gravitational forces and can be flung into different orbits. Gas clouds entering the bar are compressed and can trigger star formation. The bar plays an important role in the galaxy's current structure and evolution. Understanding when and how it formed is key to understanding the Milky Way's recent history. Evidence suggests that the bar formed relatively quickly, on timescales of a few 100 million years, and has been a stable feature of the galaxy ever since. The galactic center emits gamma rays. These high-energy photons are produced by a variety of processes, including the annihilation of dark matter particles, pulsars, supernova remnants, and cosmic rays interacting with gas. The Fermi Gamma Ray Space Telescope has detected a mysterious excess of gamma rays coming from the galactic center and the surrounding region. The source of this excess is still unknown. It could be dark matter particles annihilating each other, producing gamma rays as a byproduct. Alternatively, it could be a large population of undetected pulsars in the bulge, each contributing a small amount of gamma ray emission that adds up to the observed excess. Or it could be something else entirely. Solving this mystery is one of the goals of ongoing research. The galactic center is also a source of very high-energy gamma rays, with photons reaching energies of trillions of electron volts. These are produced by cosmic rays accelerated to extreme energies, possibly near the supermassive black hole or in the shocks of supernova remnants. Ground-based telescopes like HESS and VERITAS detect these high-energy gamma rays by observing the showers of particles they create when they hit Earth's atmosphere. The gamma ray sky looks very different from the visible light sky. Bright sources in gamma rays are often faint or invisible in visible light, and vice versa. Observing in gamma rays reveals high-energy processes invisible at other wavelengths. The Milky Way's rotation curve is flat. In a typical system where most of the mass is concentrated at the center, you'd expect objects farther out to orbit more slowly, following Kepler's laws. In the solar system, for example, Mercury orbits the Sun much faster than Neptune. But in the Milky Way, stars in the outer regions orbit at roughly the same speed as stars closer in. This flat rotation curve is one of the strongest pieces of evidence for dark matter. The visible matter alone, stars, gas, and dust, can't account for the observed orbital speeds. There must be additional, invisible mass distributed throughout the galaxy, extending far beyond the visible disk. This dark matter provides the extra gravity needed to keep stars in the outer regions moving as fast as they do. Without dark matter, stars farther out should orbit more slowly, and the rotation curve should decline. The fact that it doesn't is compelling evidence that dark matter exists. The flat rotation curve was first observed in the 1970s by astronomers like Vera Rubin and Kent Ford, who measured the velocities of stars and gas at various distances from the galactic center. Their work was revolutionary, establishing dark matter as a necessary component of galaxies and the universe. The Milky Way is part of the Virgo supercluster. This is a larger structure containing thousands of galaxies, including the local group. The Virgo supercluster spans about 110 million light-years. At its heart is the Virgo cluster, a dense collection of over 1,000 galaxies about 54 million light-years away. The Milky Way, along with the rest of the local group, is on the outskirts of this supercluster, falling slowly toward the Virgo cluster under the pull of its gravity. However, recent research suggests we're actually part of an even larger structure called Laniakea, which includes the Virgo supercluster and several others. Laniakea, which means immense heaven in Hawaiian, spans about 520 million light-years and contains about 100,000 large galaxies. It's defined not by the positions of galaxies, but by their motions. All galaxies in Laniakea are moving toward a central region called the Great Attractor. The discovery of Laniakea in 2014 redefined our understanding of large-scale structure in the universe and our place within it. These superclusters are among the largest structures in the universe, surpassed only by the cosmic web itself, the vast network of filaments and voids that permeates the cosmos. The Milky Way is moving through space at about 600 kilometers per second. This motion is relative to the cosmic microwave background, the faint radiation left over from the Big Bang. The galaxy's motion is the combined result of several influences: the local group's motion toward the Virgo cluster, the pull of more distant structures like the Great Attractor and the Shapley supercluster, and the overall expansion of the universe. From our perspective inside the galaxy, we can't feel this motion. Everything around us, the sun, the stars, the gas clouds, is moving together, so there's no relative motion to detect locally. But astronomers can measure the galaxy's motion by observing the dipole anisotropy in the cosmic microwave background, a slight difference in temperature between opposite directions in the sky caused by our motion relative to the CMB. This motion has been precisely measured by satellites like COBE, WMAP, and Planck. The Milky Way's motion through space is part of the overall cosmic flow, driven by the gravitational attraction of mass concentrations in the universe. On the largest scales, galaxies are moving toward regions of higher density, following the gradients in the cosmic web. The Milky Way contains about 10 billion Earth-like planets. This is an estimate based on the number of stars in the galaxy and the frequency of planets discovered around other stars. About 20% of Sun-like stars have planets in their habitable zones, where conditions might allow liquid water to exist on the surface. Given that the Milky Way contains tens of billions of Sun-like stars, the number of potentially habitable planets is enormous. Of course, being in the habitable zone doesn't guarantee life. A planet needs more than the right temperature. It needs an atmosphere, liquid water, a stable climate, and probably many other conditions we don't fully understand. But the sheer number of candidates suggests that if life can arise, it has probably happened many times in our galaxy. The discovery of thousands of exoplanets over the past 2 decades has revolutionized our understanding of planetary systems and the prevalence of planets in the galaxy. Data from missions like Kepler and TESS show that planets are common, with most stars hosting at least one planet. Some of these planets are Earth-sized and orbit in the habitable zone. Whether any harbor life is unknown, but the statistics suggest we're not alone. The Milky Way's magnetic field is weak but extensive. It permeates the entire galaxy, aligned roughly with the spiral arms. The field strength is only a few microgauss, about 1,000,000 times weaker than Earth's magnetic field at the surface. Despite its weakness, the galactic magnetic field plays an important role. It influences the motion of charged particles, affects the structure of the interstellar medium, and plays a role in star formation by providing support against gravitational collapse. Cosmic rays, high-energy particles produced by supernovae and other energetic events, spiral along the magnetic field lines, trapped within the galaxy for millions of years before escaping into intergalactic space. The galactic magnetic field is generated by dynamo processes, where the motion of charged particles in the disk creates electric currents, which in turn create magnetic fields. The details are complex and not fully understood, but observations using radio telescopes and measurements of polarized light from distant sources have mapped the field's structure. The field is organized on large scales, with coherent patterns spanning thousands of light years, but it also has turbulent, tangled components on smaller scales. Understanding the galactic magnetic field is important for understanding the physics of the interstellar medium and the propagation of cosmic rays. The Milky Way emits radio waves. These come from a variety of sources: pulsars, supernova remnants, regions of ionized gas, and synchrotron radiation from relativistic electrons spiraling in magnetic fields. Radio astronomy has been crucial for mapping the structure of the Milky Way. Radio waves pass through dust clouds that block visible light, allowing astronomers to observe regions that are otherwise hidden. The 21-centimeter line, emitted by neutral hydrogen when its electron flips spin, is particularly useful. This line is ubiquitous in the galaxy, produced by hydrogen gas throughout the disk and halo. By mapping the distribution and motion of hydrogen using 21 cm observations, astronomers have traced the spiral arms and measured the galaxy's rotation curve. Radio telescopes have also detected complex structures like filaments of gas near the galactic center, bubbles blown by stellar winds and supernovae, and the diffuse emission from the galactic plane. The radio sky looks very different from the visible light sky. Many bright radio sources are faint or invisible in visible light, and vice versa. Combining observations at multiple wavelengths provides a more complete picture of the galaxy. The oldest stars in the Milky Way are found in the halo. These stars, known as population II stars, are metal poor, containing very few elements heavier than hydrogen and helium. They formed early in the galaxy's history, before supernovae had enriched the interstellar medium with heavy elements produced through nucleosynthesis. Some of these stars are nearly as old as the universe itself, with ages of 13 to 13.6 billion years. Studying them provides insights into the conditions in the early galaxy and the processes that led to its formation. Population II stars have different orbital properties than younger stars. They're found in the halo and bulge, not the disk, and they have highly elliptical orbits with large velocities perpendicular to the galactic plane. This is evidence that they formed before the disk settled into its current configuration. The oldest stars are also chemically primitive, with compositions that reflect the conditions shortly after the Big Bang. By analyzing their spectra, astronomers can measure the abundances of light elements like lithium, which provides a test of Big Bang nucleosynthesis. The oldest stars are living fossils, witnesses to the early universe. The youngest stars are found in the spiral arms. These population I stars, which include the Sun, are metal-rich compared to the ancient halo stars. They formed more recently, from gas that had been enriched by multiple generations of supernovae. The presence of heavy elements in these stars indicates that they formed from recycled material, gas that had once been part of earlier stars. The spiral arms are where this recycled gas is compressed and collapses to form new stars. The arms contain bright blue stars, hot and massive, which formed only a few million years ago. These stars are so bright they dominate the visible appearance of the spiral arms, even though they represent only a small fraction of the total stellar population. The youngest stars are often still surrounded by remnants of the clouds they formed from, creating the beautiful nebulae visible in telescopes. Over time, stellar winds and radiation from the young stars will disperse the remaining gas, revealing the newborn stars. The spiral arms are dynamic regions, constantly forming new stars and destroying the clouds that gave birth to them. The Milky Way's bulge is a dense, elliptical concentration of stars. It surrounds the galactic center and contains some of the oldest stars in the galaxy, with ages comparable to the halo stars. The bulge is about 10,000 light-years across and is home to billions of stars, though the exact number is uncertain due to the heavy obscuration by dust. The bulge is more chaotic than the disk. Stars in the bulge have more random orbits, moving in all directions rather than the orderly, circular paths seen in the disk. This random motion is evidence that the bulge formed early in the galaxy's history, possibly from the merger of smaller galaxies or the collapse of gas during the galaxy's formation. The bulge has a boxy or peanut shape when viewed from the side, caused by the central bar. The bar's gravitational influence distorts the orbits of stars in the bulge, creating this distinctive shape. Observations in infrared, which can penetrate the dust obscuring the bulge, have revealed its structure in detail. The bulge is a relic of the early Milky Way, preserving information about the galaxy's formation and early evolution. The Sun will not always be in the same spiral arm. As it orbits the galaxy, it moves in and out of spiral arms. These passages occur every few tens of millions of years. When the Sun passes through a spiral arm, the solar system is exposed to a higher density of gas and dust, and the night sky from Earth would contain more bright, young stars. Some scientists have speculated that these passages might affect Earth's climate by increasing the solar system's exposure to cosmic rays, which could influence cloud formation. Others have suggested that passing through spiral arms might increase the rate of comet impacts by disturbing the Oort cloud. However, the evidence for such effects is weak, and most astronomers are skeptical. The spiral arms are not as dense or as disruptive as early theories suggested. The Sun's passages through them are relatively uneventful, with no dramatic consequences for Earth. Still, the idea captures the imagination, the notion that Earth's climate and geological history might be influenced by the galaxy's structure, connecting life on Earth to the broader cosmos. The Milky Way has a corona. This is a diffuse, hot halo of gas extending far beyond the visible disk. The corona is extremely tenuous, with densities far lower than the best vacuum achievable on Earth, but it contains a significant amount of mass, perhaps as much as all the gas in the disk. The gas in the corona is hot, heated to temperatures of millions of degrees, possibly by energy from supernovae and stellar winds. The corona is difficult to observe directly because it's so tenuous and hot. It emits X-rays, but the emission is faint and spread over a large area. Its presence has been inferred from its effects on light from distant quasars passing through it. The corona absorbs some wavelengths of light, leaving absorption lines in the quasar spectra that reveal the corona's temperature, density, and composition. The corona plays a role in the galaxy's gas cycle, serving as a reservoir of hot gas that can cool and fall back onto the disk, replenishing the gas supply and fueling star formation. This accretion of gas from the corona helps explain why the Milky Way continues to form stars despite having converted much of its original gas supply into stars over billions of years. The Milky Way is losing gas. Gas is being blown out of the disk by stellar winds and supernova explosions, escaping into the halo and beyond. These outflows, called galactic winds, can reach velocities of hundreds or even thousands of kilometers per second. The winds carry energy and material away from the star-forming regions, enriching the halo and the intergalactic medium with heavy elements. At the same time, the galaxy is accreting gas from the intergalactic medium, pulling in material from its surroundings through gravity. This infalling gas is mostly pristine, with few heavy elements, and helps replenish the gas supply for star formation. The balance between outflows and inflows determines whether the galaxy grows or shrinks over time. Currently, the Milky Way appears to be in rough equilibrium, with outflows roughly balanced by inflows. But this balance may shift in the future, especially after the merger with Andromeda, which will disrupt the gas dynamics and likely trigger intense outflows that expel much of the remaining gas. The Fermi bubbles are enormous structures extending above and below the galactic plane. Discovered in 2010 by the Fermi Gamma Ray Space Telescope, these bubbles are about 25,000 light-years tall, reaching far into the galactic halo. They emit gamma rays and may have been created by a burst of activity from the supermassive black hole at the galactic center, perhaps 2 to 3 million years ago. During this burst, Sagittarius A may have been actively accreting gas, creating jets that punched through the disk and inflated the bubbles. Alternatively, the bubbles could be the result of intense star formation in the central region, with numerous supernova explosions collectively driving the outflow. The bubbles are still not fully understood, and their discovery was a surprise. They show that the galactic center has been more active in the recent past than it appears today. The bubbles are also visible in X-rays and radio waves, indicating they contain hot gas and relativistic particles. Studying the bubbles provides insights into the history of the galactic center and the processes that drive galactic winds. The Milky Way contains about 100 billion planets. This estimate comes from the fact that most stars have planets. Data from the Kepler Space Telescope and other planet-hunting missions suggest that on average, each star hosts at least one planet. Given that the Milky Way has between 100 and 400 billion stars, the number of planets is staggering, likely exceeding the number of stars. These planets range from hot Jupiters orbiting close to their stars to icy worlds in the outer reaches of planetary systems and everything in between. Rocky planets similar to Earth are common, especially around red dwarf stars, which are the most numerous type of star. The sheer number of planets raises profound questions about the prevalence of life and intelligence in the galaxy. If even a tiny fraction of planets harbor life, there could be millions or billions of inhabited worlds in the Milky Way. The galactic habitable zone is the region where Earth-like planets are most likely to support life. Too close to the galactic center, and the environment is hostile, high levels of radiation, frequent supernova explosions, and gravitational disturbances from the dense concentration of stars. Too far out, and there may not be enough heavy elements to form rocky planets. The galactic habitable zone is thought to be a ring-shaped region between about 13,000 and 33,000 light-years from the center. The Sun, at 26,000 light-years out, sits comfortably within this zone. This location may have been crucial for the development of life on Earth, providing a stable environment with moderate radiation levels and sufficient heavy elements to form planets. The concept of a galactic habitable zone is still debated. Some scientists argue that life could arise in a wider range of environments than traditionally thought. Others point out that even within the habitable zone, many factors affect a planet's suitability for life, and location alone doesn't guarantee habitability. Still, the idea provides a useful framework for thinking about where to search for life in the galaxy. The Milky Way is a relatively quiet galaxy. It's not undergoing a major merger, and its central black hole is not actively consuming large amounts of matter. Many galaxies have active galactic nuclei, where the central black hole is accreting gas and emitting enormous amounts of radiation, sometimes outshining the entire galaxy. The Milky Way's black hole, by contrast, is quiescent, emitting only faint radiation. It occasionally flares up, as evidenced by the Fermi bubbles and other structures, but most of the time it's quiet. This is fortunate for life. An active galactic nucleus would bathe the galaxy in radiation, making it inhospitable to life over large regions. The Milky Way's relative quiescence has allowed life to develop on Earth without being sterilized by intense radiation from the galactic center. However, the Milky Way may have been more active in the past, and it may become active again in the future, especially during and after the merger with Andromeda. The Milky Way is about 1 trillion times the mass of the Sun. This includes all the stars, gas, dust, and dark matter. The visible matter, stars, and gas accounts for about 100 billion solar masses. The rest is dark matter, distributed throughout the galactic halo and extending far beyond the visible disk. The exact mass is difficult to measure because we can't directly observe dark matter. Estimates are based on the motions of stars and gas, which reveal the total gravitational influence of all the matter in the galaxy, both visible and invisible. Different methods give slightly different results, and the mass is still somewhat uncertain. Recent estimates suggest the Milky Way's total mass is between 800 billion and 1.5 trillion solar masses, with dark matter dominating. The mass of the Milky Way is important for understanding its dynamics, its gravitational influence on nearby galaxies, and its fate. A more massive galaxy will have a stronger gravitational pull, affecting the orbits of satellites and the eventual merger with Andromeda. The Milky Way's disk is divided into a thin disk and a thick disk. The thin disk, where the Sun resides, is about 1,000 light-years thick and contains young stars, gas, and active star-forming regions. Most of the stars in the thin disk are less than a few billion years old, and they follow nearly circular orbits in the galactic plane. The thick disk, above and below the thin disk, is about 3,000 light-years thick and contains older stars, typically 8 to 10 billion years old. These stars have higher velocities perpendicular to the plane, causing them to bob up and down as they orbit, crossing through the galactic plane every few tens of millions of years. The thick disk stars also have different chemical compositions than thin disk stars, with slightly lower abundances of heavy elements. The origin of the thick disk is still debated. It may have formed from stars kicked out of the thin disk by gravitational interactions with giant molecular clouds or spiral arms. Alternatively, it may be the remnant of a satellite galaxy that merged with the Milky Way billions of years ago, its stars now mixed into the galactic disk. Understanding the thick disk is important for understanding the galaxy's formation and early evolution. The Milky Way has experienced at least one major merger. About 10 billion years ago, a galaxy called Enceladus collided with the Milky Way. This merger added stars to the halo and possibly contributed to the formation of the thick disk. Evidence for the merger comes from the motions and chemical compositions of stars in the halo, which show patterns consistent with having originated in a separate galaxy. The stars from Enceladus have distinctive orbital properties. They move on elongated orbits tilted relative to the galactic plane, and they can be identified in surveys like Gaia. The merger likely triggered a burst of star formation in the Milky Way, adding to the population of stars in the disk and bulge. It may also have affected the galaxy's structure, puffing up the disk and contributing to the formation of the thick disk. The Enceladus merger is the most significant collision in the Milky Way's recent history, but it was probably not the only one. The galaxy has likely experienced dozens of smaller mergers over its lifetime, each adding mass and altering its structure. The Milky Way's spiral arms are named. The two major arms are called the Scutum Centaurus arm and the Perseus arm. Smaller arms and segments include the Norma arm, the Sagittarius arm, also called the Carina Sagittarius arm, and the Orion arm, where the Sun is located. These names are based on the constellations in which the arms appear when viewed from Earth. The arms are not distinct structures with sharp boundaries. They're density enhancements, regions where stars and gas are slightly more concentrated than in the interarm regions. The boundaries between arms are gradual, and determining exactly where one arm ends and another begins is somewhat arbitrary. Different studies have used different methods to trace the arms, leading to variations in the exact positions and names. But the overall spiral structure is clear, and the arms are prominent features of the galaxy, visible in maps of gas and young stars. The Milky Way is invisible from most of Earth's surface. Light pollution from cities washes out the faint glow of the galaxy, making it impossible to see from urban or suburban areas. To see the Milky Way, you need to be in a dark location, far from artificial lights on a moonless night. Even then, you need clear skies and time for your eyes to adapt to the darkness. Under ideal conditions, from a truly dark sight, the Milky Way appears as a luminous band stretching across the sky, dense with stars and punctuated by dark lanes of dust. It's one of the most beautiful sights in nature, a reminder of our place in the cosmos. To the naked eye, it looks like a cloud or a river of light. Through binoculars or a small telescope, it resolves into countless individual stars, too many to count, packed so densely they blend into a glowing fog. The view varies depending on where you are on Earth and what time of year you observe. The galactic center is visible from the southern hemisphere and from mid-northern latitudes during summer. It's the brightest and densest part of the Milky Way, bulging above the horizon in the constellation Sagittarius. The view toward the anti-center, in the opposite direction, shows the outer regions of the galaxy, fainter and more diffuse. Light pollution is increasing worldwide, and fewer people have access to truly dark skies. Many people have never seen the Milky Way, a profound disconnection from the night sky that humans have observed for thousands of years. The Milky Way is moving toward the Great Attractor. This is a gravitational anomaly in the direction of the Hydra Centaurus supercluster, about 250 million light-years away. The Great Attractor is pulling the Milky Way and thousands of other galaxies toward it at a speed of about 600 kilometers per second. The exact nature of the Great Attractor is unclear because it's located behind the galactic plane, obscured by the Milky Way's disk. Early observations in the 1970s and 1980s detected this motion, but couldn't pinpoint the source. More recent surveys have revealed that the Great Attractor is part of a larger structure, the Laniakea supercluster, and the motion is driven by the combined gravitational pull of many galaxy clusters in that region. The discovery of the Great Attractor and the mapping of large-scale flows of galaxies have revealed that the universe is more structured and dynamic than previously thought. Galaxies are not simply receding from each other due to the expansion of the universe. They're also moving toward concentrations of mass, following the gravitational landscape of the cosmos. The Sun is moving relative to nearby stars. This motion is called the solar apex, and it's directed toward the constellation Hercules. The Sun is moving at about 20 kilometers per second relative to the average motion of nearby stars, a velocity known as the peculiar velocity. This motion is the result of the Sun's orbit around the galaxy combined with the random motions of stars in the local neighborhood. Over thousands of years, this motion will change the patterns of constellations as stars slowly shift positions relative to each other. The constellations we see today are not permanent. They're temporary alignments that will change and dissolve over time. In 50,000 years, the Big Dipper will look noticeably different, its familiar shape distorted by the relative motions of its stars. In a few 100,000 years, the constellations will be unrecognizable. The Sun's motion through the galaxy also affects the solar system's environment. As the Sun moves, it encounters different regions of the interstellar medium, sometimes passing through denser clouds and sometimes through emptier voids. These changes can affect the solar wind, the heliosphere, and potentially even Earth's climate, though the effects are small. The Milky Way's total luminosity is about 25 billion times the Sun's. This is the combined light output of all the stars in the galaxy. The brightest individual stars contribute significantly to this total, but the vast majority of the light comes from the enormous number of average stars. If you could view the Milky Way from outside, from a distance of a few million light-years, it would appear as a bright spiral galaxy, similar to Andromeda but viewed from a different angle. Photographs of spiral galaxies taken by telescopes give us an idea of what the Milky Way looks like from afar. The galaxy M74, for example, is thought to be similar in size and structure to the Milky Way. It's a beautiful spiral with well-defined arms and a bright central bulge. The Milky Way would look similar, a grand spiral island in the darkness of space. The luminosity of the galaxy is dominated by visible light, but it also emits radiation at other wavelengths, infrared from cool stars and dust, ultraviolet from hot young stars, X-rays from neutron stars and black holes, and radio waves from various sources. The total energy output across all wavelengths is immense, powered by the fusion reactions in billions of stars. The Milky Way is part of a cosmic web. Galaxies are not randomly distributed through space. They're arranged in a vast network of filaments and walls, separated by enormous voids. This cosmic web is the largest-scale structure in the universe, shaped by the gravitational collapse of dark matter in the early universe. The Milky Way sits in a filament of the cosmic web, a thread of galaxies stretching across hundreds of millions of light years. Matter flowed along these filaments as the universe expanded, accumulating into galaxies and galaxy clusters. The voids, regions where few galaxies are found, are not truly empty but contain very little matter. They're the bubbles in the cosmic foam, surrounded by walls of galaxies. The cosmic web was predicted by theory and confirmed by observations. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the web's structure in stunning detail. The web is a fossil from the early universe, preserving the imprint of tiny density fluctuations that existed shortly after the Big Bang. Understanding the web helps us understand the formation and evolution of galaxies and the large-scale structure of the cosmos. The Milky Way's stars have a range of ages. The oldest stars in the halo and bulge are about 13 to 13.6 billion years old, nearly as old as the universe. The youngest stars in active star-forming regions like the Orion Nebula are only a few million years old, newborns on cosmic timescales. The Sun, at 4.6 billion years, is middle-aged, roughly halfway through its life. This range of ages reflects the ongoing process of star formation over the galaxy's lifetime. New stars are continuously being born from gas clouds, while old stars die, returning material to the interstellar medium. The galaxy is a living system, recycling matter through generations of stars. The age distribution of stars in different parts of the galaxy tells us about the history of star formation. The halo and bulge contain mostly old stars, indicating that star formation occurred early in these regions and then largely ceased. The disk contains stars of all ages, from ancient to newborn, showing that star formation has been continuous in the disk. The presence of old, metal-poor stars in the halo tells us that the galaxy formed from the collapse of primordial gas enriched by the first generation of stars. The presence of young, metal-rich stars in the disk tells us that the galaxy has been recycling material for billions of years. The Milky Way contains stellar remnants. When stars die, they leave behind white dwarfs, neutron stars, or black holes, depending on their initial mass. The Milky Way contains billions of white dwarfs, the remnants of low and medium-mass stars like the Sun. These white dwarfs are slowly cooling, gradually fading over billions of years. The galaxy also contains tens of millions of neutron stars, the remnants of massive stars that exploded as supernovae. Most neutron stars are difficult to detect because they emit little visible light, but some are pulsars, beaming radiation toward Earth and revealing their presence. The galaxy also contains perhaps 100 million stellar mass black holes, the remnants of the most massive stars. These black holes are even harder to detect than neutron stars. They're invisible unless they're accreting matter from a companion star, which causes the infalling gas to heat up and emit X-rays. Only a few dozen stellar mass black holes have been directly detected in the Milky Way, but gravitational wave observations have revealed that black holes are common in the galaxy. The Milky Way's interstellar medium is not uniform. It consists of multiple phases with different temperatures and densities. The coldest phase is molecular clouds, where temperatures are only 10 to 20 Kelvin and densities can reach thousands of particles per cubic centimeter. These are the birthplaces of stars. The cool phase is neutral atomic hydrogen, with temperatures around 100 Kelvin and densities of about 10 to 100 particles per cubic centimeter. The warm phase is ionized gas, heated by stellar radiation and supernovae, with temperatures around 8,000 Kelvin and densities of a few tenths of a particle per cubic centimeter. The hot phase is gas heated to millions of Kelvin by supernova shockwaves, with densities of only about 0.01 particles per cubic centimeter. These phases coexist, occupying different volumes in the galaxy. Molecular clouds are compact and dense. The hot gas fills large bubbles and cavities. The different phases interact, with hot gas expanding and compressing cooler gas, and cooler gas condensing out of the hot medium. This dynamic interstellar medium is essential for the ongoing evolution of the galaxy, serving as the reservoir of material for star formation and the sink for material returned by dying stars. The Milky Way's chemical composition has evolved over time. When the galaxy first formed, it consisted almost entirely of hydrogen and helium, the primordial elements created in the Big Bang. There were trace amounts of lithium and beryllium, but essentially no heavier elements. Over billions of years, stars have fused lighter elements into heavier ones, and supernovae have scattered these heavy elements into space, enriching the interstellar medium. Each generation of stars starts with a slightly higher concentration of heavy elements, or metals, as astronomers call them in astronomy. Everything heavier than helium is a metal, even elements like carbon and oxygen. The Sun's metal content is about 2% by mass, higher than the ancient halo stars, which have metal contents of only 0.001% to 0.1%. This reflects the enrichment of the interstellar medium over the 9 billion years between when the halo stars formed and when the Sun formed. The ongoing enrichment continues today, as massive stars explode and seed the galaxy with freshly made elements. In the future, the metal content of new stars will be even higher, assuming star formation continues. The Milky Way is approximately 100,000 light-years across. This measurement refers to the diameter of the visible disk, where most of the stars reside. But the galaxy extends much farther when you include the halo and the dark matter halo. The stellar halo, containing globular clusters and old stars, extends out to at least 200,000 light-years. The dark matter halo may extend several 100,000 light-years from the galactic center, possibly even farther, encompassing a much larger volume than the visible galaxy. Defining the edge of the galaxy is difficult because the density of matter gradually decreases as you move outward, with no sharp boundary. The visible disk has a fairly well-defined edge where the density of stars drops off sharply, but the halo and the dark matter halo fade gradually into the intergalactic medium. Satellites like the Magellanic Clouds, orbiting at distances of 160,000 to 200,000 light-years, are still considered part of the Milky Way system, bound by its gravity. The Milky Way's influence extends even farther, affecting the motions of galaxies and gas out to distances of several 100,000 light-years. The Milky Way has produced about 1,000 supernovae in its history. These are the explosions of massive stars at the ends of their lives. Supernovae are rare events in any given galaxy, occurring perhaps once or twice per century. Over the Milky Way's 13.6 billion-year history, that adds up to thousands of explosions, perhaps tens of thousands. Each supernova releases an enormous amount of energy, briefly outshining the entire galaxy in some wavelengths. Supernovae enrich the interstellar medium with heavy elements, synthesized in the cores of massive stars and in the explosion itself. Elements like gold, platinum, and uranium are created in supernovae, along with more common elements like oxygen, silicon, and iron. Supernovae also trigger the formation of new stars by compressing nearby gas clouds, creating shock fronts that can initiate collapse. And they leave behind remnants, expanding shells of hot gas, and at the center, a neutron star or black hole. The last supernova visible to the naked eye in the Milky Way was Kepler's supernova in 1604. Since then, there have been no confirmed supernovae in the galaxy visible from Earth, though several may have occurred on the far side, hidden by dust. The Milky Way has an estimated 100 million black holes in its central region alone. These are stellar mass black holes, the remnants of massive stars. They're extremely difficult to detect unless they're actively accreting matter, which causes them to emit X-rays. Most black holes are isolated and invisible, drifting silently through the galaxy. But they're there, contributing to the galaxy's mass, and occasionally revealing themselves when they interact with a companion star or pass close to another object. The number of black holes in the Milky Way is estimated based on the rate of massive star formation over the galaxy's history and the fraction of massive stars that leave behind black holes rather than neutron stars. The estimates are uncertain, but they suggest there could be as many as 100 million stellar mass black holes in the galaxy. Most will never be detected, remaining hidden in the darkness, but each one is a cosmic fossil, the compressed core of a star that once shone brightly and then died in a catastrophic collapse. The Milky Way's metallicity gradient shows that the outer regions are less enriched. Stars near the galactic center have higher concentrations of heavy elements than stars in the outer disk. This gradient reflects the history of star formation in the galaxy. Star formation has been more intense near the center, leading to more cycles of stellar birth and death, and thus more enrichment. The outer regions, where star formation has been slower, have undergone fewer cycles and remain less enriched. The Sun's metallicity is typical for its location in the galaxy, about halfway out from the center. This metallicity gradient is observed in many spiral galaxies and is a natural consequence of how galaxies evolve. Gas flows inward over time, accumulating near the center where it forms stars more rapidly. The enriched gas mixes throughout the disk, but the center remains more enriched than the outer regions because of the higher rate of star formation and supernovae. The Milky Way is on the Tully-Fisher relation. This is an empirical relationship between a galaxy's luminosity and its rotation speed. More luminous galaxies rotate faster. The relationship was discovered by astronomers Brent Tully and Richard Fisher in 1977 and has been used extensively to estimate the distances to galaxies. The Milky Way fits this relationship, which is based on the idea that a galaxy's luminosity is closely tied to its total mass, including dark matter. Faster rotation implies more mass, which in turn implies more stars and thus more light. The Tully-Fisher relation is one of several scaling relations that describe the properties of galaxies. Understanding why these relations exist and why galaxies follow them helps astronomers understand the processes that govern galaxy formation and evolution. The Milky Way's escape velocity at the Sun's location is about 550 kilometers per second. This is the minimum speed an object would need to escape the galaxy's gravitational pull from our position. Any object moving slower than this will remain bound to the galaxy, orbiting the galactic center indefinitely. Objects moving faster than the escape velocity will eventually leave the galaxy, though it would take tens of millions of years to reach intergalactic space even at these speeds. A few stars, called hypervelocity stars, are moving fast enough to escape the galaxy. These stars were likely flung out by gravitational interactions near the supermassive black hole at the galactic center. When a binary star system wanders too close to Sagittarius A, one star can be captured while the other is ejected at high speed, sometimes exceeding 1,000 kilometers per second. Dozens of hypervelocity stars have been discovered, most of them heading out of the galaxy and into intergalactic space. In a few million years, they'll leave the Milky Way entirely, solitary wanderers in the void between galaxies. We've covered a lot of ground tonight, from the dense core to the sparse halo, from the ancient stars that remember the galaxy's birth to the newborns still glowing in their natal clouds, from the supermassive black hole at the center to the dark matter extending far beyond the visible disk. 100,000 light-years across, containing hundreds of billions of stars, over 13 billion years old. But here's the thing, you're not separate from any of this. The Milky Way isn't just a galaxy you live in, it's part of you. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged inside stars that lived and died within this galaxy. Those stars scattered their elements into space when they died, enriching the gas clouds that eventually collapsed to form the sun and planets, including Earth, including you. Every atom in your body heavier than hydrogen is a piece of the Milky Way's history, a fragment of stars that burned billions of years ago. The carbon in your cells was created in red giants through the triple alpha process. The iron in your blood was forged in the final moments before a supernova explosion. The oxygen you breathe was produced in massive stars that lived for only a few million years before dying violently. These atoms have journeyed through the galaxy for billions of years, cycling through stars, gas clouds, and eventually planets before coming together to form you. You're not just living in the Milky Way, you're made of the Milky Way. Every breath connects you to the interstellar medium. Every heartbeat pulses with atoms from ancient stars. When you look up at the night sky and see the Milky Way stretching overhead, you're not looking at something distant and separate. You're looking at home. You're looking at the system that created you, the galaxy that shaped the sun and Earth, the cosmic recycling system that made life possible. The sun is orbiting this galaxy at 828,000 kilometers per hour, carrying Earth and everything on it around the galactic center. You're moving through space right now at incredible speed, part of the Great Wheel, one tiny part of the vast system we call the Milky Way. And you're connected to all of it, to the spiral arms, to the dark matter halo, to the supermassive black hole at the center, to every star that ever lived and died in this galaxy. You're part of the story, a thread in the tapestry, a note in the cosmic symphony. If you're still awake, there are more videos waiting. But if sleep found you somewhere along the way, then this worked exactly as it should. Rest well knowing you're not just in the galaxy, you are the galaxy, experiencing itself, looking back at itself, understanding itself. See you next time.